Right. Good afternoon, everyone. Today's class we're going to be doing a little bit of review, but before we jump into that, let's just to keep it in our heads before we go into spring break. Let's just quickly review what we did last class. The winding diagram, and then we'll take a little bit look into how the commutator changes the current from one winding to the other as it transitions. And it will probably take 15 to 20 minutes. Once we're done with it, we'll start with doing a little bit of review, right? So, this is basically the question that's asked in homework 5, which is due the Thursday after spring break. Please don't work during the spring break. 4 days is more than sufficient to complete it. Once you come back from spring break, you can just get started. So in the class, we looked at the case where we have 6 slots on the rotor, right? So this is basically a cylindrical structure with slots stamped into them. And the way we are looking at it is completely opened out so that we can trace the winding diagram. In a circular manner, it's a little bit difficult to trace it. So whenever winding diagrams are drawn, it's typically drawn in this way. So in the homework, it's just a difference. Here we have 6 slots, in the homework, it's 8 slots. Right? We use the same simplex lap winding full pitch in the homework as well. In the project that I will be assigning 1 week after the spring break, you will be doing a short pitch winding, which we haven't taught in class, but you'll try and figure it out on your own. Right? Okay. So it's a 6 slot winding, 6 slot rotor. Can you really tell me what is the difference between the slot of the first conductor and then the forward conductor that's connected to it? If it's a full pitch winding. Well, what do I mean by full pitch? Does the term full pitch mean? Anybody? So when we do a full 180 degree, so when we have 6 slots on the rotor, when we start from the first slot and go all the way 180 degree back, that's called a full pitch. Right? That will generate the maximum amount of EMF in the motor under ideal conditions. So there are other options. Instead of going one full 180 degree, you can close it off in another area, right? In which case you won't generate the full 180. So when we had a rotor structure, it's my very crude drawing of looks awful. So let's say this is a rotor with the 6 slots stamped into them. The first winding starting here must go all the way to the back and come back. So that will be a full pitch winding. Alternative is to take the first winding starting here, and you can instead go 1 slot behind. That will be a short pitch. But this would have some disadvantage and some advantages too. But the problem is when we have our poles, north and south pole, if you look at this winding that's full pitched, once it starts to turn, there will always be one winding that's under the north pole and another winding that's under the south pole. So you'll get maximum amount of EMF that's being generated, maximum amount of torque that's being generated. But in this case, where it's short pitch, 2 set of conductors can remain under the same pole for a small portion of time. Right? So let's say this rotates 10 degrees in this direction. Both these 2 conductors would be on the north pole. Right? So it's not producing the same amount of torque as having them 180 degree diametrically opposite. So that will be the disadvantage. When you look at short pitch winding for the project, you kind of argue and figure out the reason for why people still do it. Once we cover armature reaction after spring break, you'll get an idea of it, right? So we have 6 slots, and that means in a full pitch winding, if the number of slots is n, then the forward direction, the slots must be 3 slots apart, right? So if it's 6, then I need to put the forward conductor in 3 slots starting from the first slot. So first slot, I have conductor 1, and if you look at where it goes back into the backward side, it will be 3 slots ahead. So S1 plus 3, they'll give you slot 4, and then you would close it, and then you would bring it back and to push it 1 slot forward, right? So the act of bringing it backwards, this is called lap winding. So each of those terms means something. So full pitch means in the forward direction, we jump slots by n by 2, where n is the number of slots. Right? That's what the term full pitch means. Lap winding means when the winding goes in the forward direction like this, you have two options. Either you can take your conductor and go in the forward direction, or you can take your conductor and come back into the backward direction. So the lap winding is the one where we go in the backward direction. The one that goes in the forward direction, it looks like a wave. So it's called a wave winding, right? So those are the two different options we can do. In this class, we are going to keep it simple. We are going to do lap winding. Lap winding is typically used for motors with typically low voltages but very high currents. So you have multiple parallel pathways with higher number of poles. In wave winding, irrespective of number of poles you have, the parallel pathways is always going to be two, right? So you would want to use it for much higher voltages. Okay, so coming back here, now again I have multiple options. I can either put it in slot 1, slot 2, or the commutator segment. So let's say there is no commutator segment here. There are multiple ways of winding this again. So I can take it to slot 2, bring it back out, take it to slot 5, and then have a commutator segment here. So this can instead be C2 instead of C1, right? Have commutator segments that are far apart. So that would be called a duplex winding. Again, we won't look into duplex winding in our class. We will be looking at what we are going to be looking at is simplex winding. So the way is you start like this, go back and come back and go to the slot ahead of it, and you would put the commutator segment here. And for the next one, you would have another commutator segment. Right? So C1, C2, so on and so forth. So every time you see a bend here, you would put a commutator segment. So that's the simplex winding. Okay. So the case we have is simplex lap winding full pitch. Right, so that's what we have there. So we are going to go forward 2 slots or 3 slots, and then we are going to come back 2 slots. So the backward logic would be n by 2 minus 1 going in the backward direction, going in the forward direction, you would do n by 2. So whenever if I instead of the homework ask you to do for 8 slots, the logic is still the same. So start off from first slot, go forward 4 slots, go back 3 slots, go forward 4 slots, go back 3 slots. Keep on doing this until you come back and terminate at the point where you began, right? And this is called, one more term, double layer. This is very straightforward to understand because each slot has 2 layers, one set of winding going in the back, one set of winding coming on the top, right? So that's the double layer definition. If it's a single layer, then you would just have conductor go up, right, and go down, but you won't have the other set of conductors in the slot. So you won't have the coming down conductor, you won't have the coming up conductor in the slot. It depends on the number of slots you have. In a DC motor, typically it's very hard to get a configuration where you can get a single layer winding. And people usually don't do it either because there are a lot of advantages that you gain by doing a double layer, including mechanical stability as the rotor starts to rotate, right? But we do see, when we go to AC motors, we will see single layer windings there. Okay. Anybody has any questions so far about the winding structure?
Did you say there was another term that was used to describe, it was like retro or something?
Oh yeah, thank you. Retrogressive and progressive. I forgot that term. So in our case, we are doing a progressive full pitch winding. So we are starting from, thank you, Ben. So let me draw it in this diagram. Ignore the change in the commutator position for now. So when I started from slot 1, I went forward to slot 4. This is called full pitch. Coming back 1 slot forward and having a commutator there, that will make it a simplex winding. Coming in the backward direction makes it a lap winding. Going forward would have been a wave winding. And then when these coils are fully arranged, they all have 1 layer on top, 1 layer on the bottom, so forming a double layer. Again, if you have a slot and you have multiple conductors which is doing 10 turns, that won't become 10 layer, right? The number of layers is basically 1 set of conductor going in one direction, other set of conductor coming in the opposite direction. If you have a slot and you do 10 turns, all the 10 conductors are going in the same direction. In the one slot and the other slot, all the 10 conductors are coming in the same direction. We would represent that as a single coil in this diagram. All right, so this is a coil diagram, not a winding, not a single wire diagram. So when I represent this coil, that means if there are 10 windings in the slot with a single loop forming a single coil, that whole thing is just represented by 1 line. So this one is a conductor going in the forward direction, coming from the bottom slot coming up. This is a conductor coming from the top going down. So that's what makes it double layer. Okay. And the concept of progressive versus retrogressive, when I come to this C2 commutator, I have two options. Either I can go to second slot or I can go to the sixth slot. Right? So if I go to the second slot, that's called progressive because the winding is going in the forward direction as I keep winding. If I go backwards, it's called a retrogressive winding. So because I'm winding the winding in a backward direction. All right, so from sixth slot, it will go to slot 3. And then from slot 3, it will go to slot 5. So it's just doing it in the reverse. Would there be any advantage with progressive winding compared to retrogressive? Absolutely nothing. Initially, it might appear as if the end turn length is larger, but that won't be the case because we are looking at it in a one-dimensional plane. When you plot it in a two-dimensional, when you plot it in the circular, instead of putting it in a plane or not one dimension, instead of putting it in plane or if you plot it in the circular way, so we are having coil starting at slot 1 and then going to slot 3, slot 4. Let's say I go in the anti-clockwise direction, 1, 2, 3, 4, 5, 6, right? Instead of going from slot 4 to slot 2, I can go from slot 4 to slot 6. So if I go from slot 4 to slot, so 1 goes to 4, then 4 to 2, this is called progressive. This is called retrogressive. That's all the differences, right? In the three-dimensional view, both the lengths are the same, whether I go to slot 2 or slot 6. Here in the one-dimensional, in the planar view, it might appear as if I go here versus here, the end turn appears longer, so copper might be wasted, but that's not the case. So the winding diagram in planar view might be misleading in some cases, right? Okay, anybody have any questions? Yeah.
So if you were designing a motor, how would you choose which way you would prefer to do it?
Random.
Random.
Whatever you want. So between retrogressive and progressive, there is no advantage. Right? It'll be the choice is whatever you want it to do.
If you number the slots differently, you could have the same
Yeah.
winding beat. Okay.
Yeah, instead of going 1, 2, 3, 4, 5, I could have gone 1, 2 in the clockwise direction. That would have been the same effect as. Yeah, that's a good analogy. Any other questions? Okay. So let's quickly look at what happens when we go from one when the rotor starts to rotate and the brushes are staying still and the commutator segments are moving past it, right? So each of these coils that I have here, these are a whole bunch of wires on an iron core. So they're going to have a whole bunch of inductance to it. And that's the reason we are representing each of those coil as a bunch of inductor, right? So this is coil 1, it's the conductor 1, conductor 2, 3, 4, that's how I have numbered it. Typically, textbook would like to number it as C1 and C1 prime or something like that, right? Totally up to you. Whichever book you use, they might have different conventions. So if coil 1, which is basically conductor 1 and conductor 8, the blue one is drawn here, conductor 1 and conductor 8, right? So the conductor 1 is connected to commutator segment 1 at the beginning and conductor 8 is connected to commutator segment 2, right? So this is C1 and this is C2, C3, C4, C5, and C6. So at this point, the current, when we send it from the outside from the motor, it can branch off into two pathways. So if I have a DC current of 20 amperes, 10 amperes splits to the left, 10 amperes splits to the right. And then 10 ampere flows in this conductor, 10 ampere flows in this conductor, 10 ampere flows in this conductor, and then comes back out here. Same happens here, 10 here, the same 10, because these are all series connected by the commutator copper. So this is short here. And then this 10 ampere goes here, comes out through this for a total of 20 ampere, right? 20 ampere went in, 20 ampere came out, we have two parallel pathways. So this is where when we have more number of poles, the parallel pathways will start to increase for a lap wound machine, so you can push more current into the motor. All right. So now what we are going to look at is we are going to look at the rotor start to rotate. So as it rotates, these windings and the commutator segments are moving with it, but the brush is remaining at the same place. So the commutator, so instead of changing the winding diagram, I'm moving the commutator in this diagram. So the brushes, I'm moving in the forward direction, but it's actually the rotor moving in the backward direction, right? So once we come to this point, we are basically shorting conductor 1 and conductor 8. Is there going to be a problem? Shorting the two conductors? Why not?
EMF is 0
Why is the EMF 0?
because the rate of change of flux is low.
Why, at what position is that in? What is the rotor winding angle? Assuming the angle of along the magnetic field is 0 degree, what angle is the coil for this configuration? 90 degree. So the magnetic field is planar like this, right? And our coil is located in this direction like this. So it has rotated from some angle, say 85 degrees to this position 90 degrees. That's when the short is happening. So this is absolutely fine because the flux is going to be maximum, but EMF is d phi by dt, right? So the EMF across the coil is 0. So there is no issue shorting this coil at this point, right? Even if it's at an angle slightly behind, as long as the EMF is small enough, it's okay shorting it because the brushes themselves have significant amount of resistance that you won't actually be shorting copper wire, right? And as these conductors keep moving backwards, so this is the position where we have shorted this. But because of the shorting, if you see now previously, 3 coils were contributing to the EMF. So if I measure the voltage across these 2 terminals, it was EMF of this coil plus EMF of this coil plus EMF of this coil. And then on the other side, EMF of this coil plus this coil plus this coil. So my EMF would have been quite large. But when the short happens, one of the coils is dropped out, right? It's basically shorted. So the current is just freewheeling through this pathway, right? And then the rest of the current is again splitting and coming out like this. But if you look at the EMF, only 2 coils are contributing to the EMF that you measure across the terminal, right? So the problem is, if you look at our EMF profile, previously it was like this. During the short, 1 coil got dropped. So the EMF would drop at that point. And then it'll again be flat and then short. So every time this commutator action happens, the EMF will start to dip a little bit, right? And that also means the torque will also drop. The coil that's producing the torque is also reducing. Thomas.
Is the current that's split up into the 2 parallel paths still roughly 10 amps each?
Yeah, it will be. Because each of these coils, no, not roughly, it will be exactly 10 amperes. Because each of these coils were previously carrying 10 amperes. And these are inductive coils. If nothing else changes, if the contact isn't changing, they are going to continue carrying the 10 ampere.
Will the shorted inductor drop?
The shorted inductor current will start to change.
Okay.
Right, we'll take this diagram, it's a little bit hard to visualize it, but when we put the planar diagram, you'll start to see. So the current will start to drop in the coil and then transfer the direction. Because let's look at the direction of the current. In this case, the current was going from conductor 1 to 8, right? Everybody clear on that? So on the left is conductor 1, on the right is conductor 8. So current is coming in from conductor 1 going into conductor 8. But once it goes to the other side, let's look at the case where the commutation is completed. Current is now going into conductor 8, coming out of conductor 1. Right? So during this path, the reason it's called commutator is because the current is actually commutating from positive polarity to the negative polarity in that one particular coil. In all the other coils, the current direction remains the same. Right? So these coils, current direction remain the same. This coil, again, the current direction had flipped. So coming out here, going in here. Previously, it was coming out of 2, going into 7. Now, if you see, it's coming out of 7, going into 2. Once the commutation is completed. So those 2 coils which get shorted, the direction of the current changes full 180 degree. Right? So that needs to happen in the commutator action. Right? Anybody any questions? Yep, John.
Does that mean like if the motor is spinning slowly enough, the effect of that EMF drop is more significant?
No. The percentage of EMF drop would be just a function of number of coils that are shorted, right? Irrespective of what speed it's rotating. So if your motor rotates fast, the EMF is going to be larger by a factor of exactly the proportionality. We derived that formula, right? E was some Ke times omega. So if you're rotating at 100 radians per second, let's say the EMF is 10 volts. If you're rotating at 200 radians per second, the EMF is 200 volts. But during this commutation process, 1/3 of the coil, in this case for a 6-slot winding, 1/3 of the coil is being shorted. So when the commutation happens, when you're rotating 100 radians per second, 10 volts would have dropped to 6.66 volts, right? 20 volts would have dropped to 16 point, whatever that comes out, like 14.44 volts, right? So it will be the same 1/3 volt that drop, 30% voltage that drop, 33% that drops. So that won't change, but the magnitude would be different because the EMF value itself is different. Okay? Any other questions? Yeah.
When you're in between C1 and C2, I understand that like the needs to progress down, understand it needs to split, but why wouldn't it take the path of least resistance and go from 1 to 8 versus going all the way around?
No, so when we have an inductor, right? So let's say, so there are 2 different pathways. Let's say we have an inductor like this, how do I draw this? Let's say I had an inductor like this with some resistance pathway. right? So let's say previously the circuit, some current is flowing through this inductor and some current is flowing through this inductor. If I short out this inductor, right, it doesn't mean the current through this inductor can go away. Because the current can't change, LdA by dt is not going to allow it to change. Right? So as long as it's an inductive coil, the current is going to continue to change through it. So when you look at this, that's why I'm talking as if it's a current source supplying 20 ampere. Because when you think of it as voltage, then there is not, the voltage is not across this coil that's creating the current through the coil. It is the current that's already in the coil, which is creating the EMF that we are seeing. All right, so it's the counter way of looking at it.
Thank you.
Yep.
Where's the energy go that's stored in those inductors? Is it going to the brushes or?
Yeah, it'll be lost in the brushes. The energy is for a portion lost. Okay. Any questions? Right, so we have this commutation process. Okay. So we're going to look at a very ideal case where there is no, the commutation is proper. And we will look at a case where it's improper commutation and what's going to happen. So looking at going back to our coil diagram, we're just going to analyze what happens in the top coil alone. So we have the circular C1, C2, C3, C4, C5, C6. We're only looking at the C1, C2 case, and we are looking at the transition of conductor 1 to 8, right? So initially, this commutator left 10 ampere went through it. On the right, 10 ampere went through it for a total of 20 ampere coming out of the coil, of the brush. So 20 ampere coming here, and it's splitting into two pathways, one going to the left, one going to the right. Right, everybody clear? This does not come out of this path because this commutator is hanging, it's not connected to the external world. C4 is the one that's connected to the external world. So this 10 ampere flows to the three coils and then comes out of C4. Okay. Now we are going to look at what happens as this brush starts to move. Once this brush moves, it's still 20 ampere, both of it is going to be equal pathway. And then once the contact is made, now the 10 ampere has multiple pathways to flow through. So this 10 ampere is going to continue to flow because this coil previously had 10 ampere. It's an inductive coil. It's not going to allow the current through the coil to change. So that is going to continue to go through it. But this pathway now, so 10 ampere split, the remaining is 10 ampere. This 10 ampere has multiple pathways through which it can split through. Okay. So how it splits is a very complex way, a complex equation that will come out of it. But our case for now, let's just look at theoretically that it's going to be proportional to the resistance of the brush versus the commutator segment that we are connected to. So right now, say 10% is making contact with the second commutator, 90% is making contact with the first commutator. So the current split would be 10 there, 90 here. All right, just looking at it as if it's purely resistive. So this current at this coil is now going to start to drop. So previously it was at 10 ampere. This current is going to start to drop. It's going to go to 9 ampere while 1 ampere starts to go out of this branch. But if you look at the total current going into the rest of the coil, that's still the same 9 plus 1, which is going to be 10 ampere. Because again, this is an inductor coil carrying current. The rest set of coils on the right, those current cannot change. Same as the reason why the current in this left set of coils cannot change. All right, but in this coil which is shorted, now there are multiple pathways for the current to split through. Let's keep continuing this process. As more and more of the portion of the brush moves towards the commutator 2, this resistance starts to drop, while this resistance starts to increase. Right? Because there is more surface area for the current to flow through, and that's what conductivity is, right? Conductivity is the surface area divided by the length, and then divided by the conductivity of your conductance of your copper ring or whatever. So, sorry, conductance is going to be area divided by length divided by some conductivity, let's call mu or something, right? So as the surface area increases, the resistance starts to drop because your conductivity is increasing. So as the resistance drops, more share of the current is going here, less share of the current is starting to go here. And we keep on continuing this process. Once the share of the contact here and here are the same, now the current would equally prefer both the pathways. So the current is going to be 10 amperes this way, 10 amperes this way. Right? And through the center coil, the current has gone to 0. So previously it was positive 10 ampere. Now the current through the center coil has gone to 0 because if you do KCL, the total current is 20 amperes. So the center conductor has to carry 0 ampere. And you can continue this process as this commutator segment moves backwards or the brush effectively relatively moving forward. Now this is having more contact area while this is having less contact area. So more current is going to flow through this segment compared to this segment. So this is going to carry 11 ampere total. This is going to carry only 9 ampere. Out of that 11 ampere, 10 ampere goes to the right because that is an inductive coil carrying the same thing. 1 ampere is going to start to flow into this conductor, which is shorted. So if you look at it, previously this coil had the current of 10 ampere in the positive value, and then it went to negative. Now it's starting to go further negative. And the commutation would be completed once the contact is fully broken. And when the break happens, we better hope that this conductor carries 10 ampere. Right? Yep, John.
Sorry, just to clarify, so we're saying that current in the middle inductor can change because it's like a lower resistance path with the brush, right?
Yep. So think of it like you have a inductive coil with some current through it, and you have some external resistance, and this resistance is increasing.
Okay.
Right? So as the resistance, it's not a perfect explanation, as I'll get to in a second, but as the resistance keeps increasing, the energy is being dropped in that resistance. So half Li square is going to drop in the coil, right? So all of that energy is dropping, then the current in the coil also starts to reduce. So that's what is happening here.
Could you have a case where it doesn't like change quickly enough and, okay.
Yep. This is a very ideal assumption because we're assuming that the whole thing is resistive in nature, but as we know, this is not resistive. Right? So I'll get to that in just a second. So conductor coil, so if you look at this, the point with which the conductor current went to zero, this was when the commutator is exactly in the middle, right? The brush is exactly in the middle of two commutator. This is the point where the coil is perfectly at 90 degree, right? So the EMF across the coil is zero. When will the current through a coil be zero if the EMF is zero? If it's purely resistive coil, right? If the EMF across the coil is zero, then the current will be zero if it's purely resistive. But the problem is that coil is inductive in nature. So when the voltage is zero, the current is definitely not going to be a zero. So we assumed it to be a purely resistive case when we are analyzing this, knowing well that the coil is inductive in nature, right? So an ideal case where the coil behaved as resistive in nature, the current would have gone to zero when the coil was at perpendicular 90 degree, which is basically the short of two commutator segments, right? And then as the EMF starts to, so once this starts to go the other direction, EMF flips around. So the current in the coil would have also started to change to the other direction. Okay. So when this transfer completely happens, hopefully the current goes to 10 ampere in this coil. So that 10 splits here, 10 splits here, and we have both equal split on both direction, right? So this is the case where we have very ideal case where when the brush is right in the middle, current goes to zero, and then the current looks beautiful like this where it transitions and has a proper commutation. But in reality, this is not what would happen as we transition. So the case, let's go right to the case where it's brushes in the middle. There is no reason just because the brush is in the middle, the current through the coil should be zero, especially if it's an inductive load. We know that, let's say we have a sinusoidal voltage in an inductor, right? The current is in fact 90 degree phase shifted. So if this is the current, this is the voltage, right? When the voltage is at its maximum, the current is at its minimum, and the voltage is at its zero, the current is at its maximum, right? So here in this case, our coil is a mix of inductive and resistive component. The resistive is not trivial. When you have just the coil alone, the resistance is trivial. But in this case, the coil is shorting through the brush, right? And the brush has quite a bit of resistance that we have there in the brush, right? So in some way, the brush aids in your commutation process. If you have a graphite brush, if you put a copper brush, it gets a little bit tricky because the resistance is very small. So it's more acts as inductive. So it gets even delayed further, right? So let's assume that it doesn't fully go to zero. There is some amount of current because of the inductive nature. The voltage has gone to zero. So in our case, so this was the case of pure L. If it was an RL network, there would be some phase shift between the current and the voltage. So when the voltage goes to zero, the current is still some tiny value, but non-negligibly non-zero value. So you can extend this process forward. Once the full thing is completed, the current needn't have fully gone to zero, right? There is still some amount of current still going through the segment, but you're suddenly interrupting the contact. It suddenly breaks out and the copper moves away. But current will always find a path. Current cannot instantaneously go to zero. So it will basically create a huge voltage across this LdI by dt. You're breaking an inductor current. LdI by dt would create a very large voltage. So here you would have some positive voltage, you would have some negative voltage, and the voltage will be so large that the air gap will get ionized and you will see a huge spark in between, right? When we come back from spring break, I'll show a video of it where we can clearly see the sparking when the commutation is not proper. And that will start to damage your graphite brush. Because every time ionization happens, there is going to be carbon that's going to get oxidized and it's going to start to break down. So carbon is going to get broken off. And that the vapor graphite is then going to go and settle on these copper brushes, and in between these segments, and over some time period will start to short out the whole commutator segment, right? So this is improper commutation. This is what we want to have ideally, but this is what would happen in reality. where the current wouldn't have commuted during this time. It would just spark and it would all come back to, it will definitely go to 10 amperes, negative 10 ampere. But the way it happens is not ideal, right? Any questions? Okay. Once we come back from spring break, we'll look at how to prevent this. We'll do a review of this again, and then we'll look at how to prevent this problem in a practical DC motor. Okay. With that, let's do a review of the first 4 homeworks. So to our first set of lectures. This is a mechanical model. Right, so where we had this some kind of generator. So initially we assumed, we didn't know how this was working. We just had to assume somehow magically was happening. But now we are starting to get a picture of what's going on inside. So there is, let's assume it's a DC motor. There's some magnets here. There's some magnets south and north. We are passing current through this, and then it experiences some torque, force, which effectively ends up being some torque. And that is the torque we are going to call as tau EM, right? Electromagnetic torque. So we have some electromagnetic torque acting on this, and let's say it's rotating along the same direction. It needn't. It can have rotate in the opposite direction too. Let's say if it rotates in the opposite direction while the torque is in this direction, what is it acting as?
Generator.
A generator, because a power from this motor, is going to be equal to tau EM times omega M, right? If both of them are positive, then it's acting as a motor. If one of them becomes negative, either this or this, it starts to become a generator. So if I ask you, if I reverse the direction and ask you what the operation is, it's going to end up behaving like a generator. And this is what we do in electric vehicles too, right? In electric vehicles, what we'll do is the direction of the speed is not changing. Speed is going to keep being the same direction. But when you apply a brake, the torque basically reverses, right? And the speed cannot suddenly change because again, it's an inertial system. Similar to an inductor, current cannot change. In an inertial system, the speed cannot suddenly change. Otherwise, d omega by dt will go to infinity, which will be problematic. So we'll reverse the direction of the current, thereby taking out energy back and recovering it so that we don't lose the energy in the braking system, right? How do I reverse this torque? Let's say EV motors are not using DC motors, but let's say it's a DC motor. How do I reverse the torque? Off. Right? We cannot change the commutator anyway. It's a physical element.
Yeah, like the contact, the brushes. I don't know.
We can't change anything mechanical. Right? This is why we have put the motor already in the car and the motor is running. You want to change the torque polarity. What was torque directly proportional to in our derivation?
Voltage. No.
What was force proportional to from Lorentz force equation?
Current.
Current. We cannot change the B field either. Once we put the magnets, the B field is fixed. There's going to be armature reaction. We will not worry about this, but the B field itself is from the magnet is not going to change. So our force is directly proportional to the current, and this is what we extended it further and further and further with some trivial derivations. We came out with the value. It was some kT times the current I. I don't remember what this is. I think it was like number of conductors times B, maybe L times cross-sectional area. I'm not sure. Don't quote me on this. But it was some constant times the current. The thing that was proportional to the voltage, so the back EMF, so the speed is proportional to the back EMF, right? So if you adjust the terminal voltage, in effect, you're adjusting the speed of the motor for the most part, ignoring the losses, drops in the resistor and inductor. That's what we did in the second class in a hardware demo, right? When I had the DC motor, I asked you what the speed response would look like as I keep increasing the terminal voltage of the DC motor. And we saw that as I increased the terminal voltage, as I kept on going to higher and higher voltage, my speed started to increase as well. As I did every step in the voltage, my speed was also increasing as steps, right? So our voltage is proportional to omega, and our current is, torque is going to be proportional to the current. So the way I change the torque is basically flipping the direction of the current, right? That in turn would mean you would have to use some kind of power electronic converter, which is basically changing the voltage so that the current can then reverse, right? But the idea is you need to flip the current direction. Okay, so we have some electromagnetic torque, and then we have some load torque that is opposing it, right? So the equation for the system, we wrote it down as tau em equal to the opposing load torque plus d omega by dt plus b times omega. This is the inertia. It was our viscous friction coefficient. Linearized viscous friction coefficient, because it can be some b omega square too, right? But again, for our case, we want to linearize it and make it as simple as possible. Okay. Let's consider a very simple case of where the load itself is purely friction. Can anybody give me an example where the load is purely a frictional load? Yep, Thomas.
I just have another question. So like, you're not changing the polarity, obviously, of like the EMF, but you're changing, by changing direction of current flow, you're inherently changing the applied voltage on the brushes, right?
Yep.
That you're flipping them.
Mhm.
Okay.
Yeah, so everybody is clear that the EMF and the terminal voltage are two different things, right? Did anybody think it was the same thing? If you think it's the same thing, that's okay to let me know, because it's a very important distinction to understand the difference between EMF and the terminal voltage. Everybody clear?
Can you cover the difference?
Right. So let's say move to the south. Can't even visualize how to draw in 3D. Okay, this coil is at some angle alpha, right? And let's say this alpha is between 0 to 90 degrees. Let's why not just give it a number. Let's say alpha is at 45 degrees, right? So as this coil starts to rotate, can somebody tell me whether the left conductor would be positive or the right conductor would be positive? So this is basically, so we have a magnet here. Again, this concept you would need to understand for the exam as well. That's not part of, don't think it's not outside of the whole, exam. We are looking at the case of a DC motor, but the polarity of EMF is necessary to understand them. So we have north here, south here, and the coil is like this, and the coil is starting to rotate, let's say from 45 degree to 50 degree. Which direction would the EMF be? Is the polarity that I've drawn here correct? No? Why not, Thomas?
Field lines are that way, and so that's where my thumb goes. Then the current goes the other way, and current goes from high to low.
But you're mixing up two independent quantities though. The field lines are created by a magnet.
Okay.
So you would curl your hand along the magnetic field. So if you had a current carrying conductor, and let's say I give you a magnetic field that looks like this, right? If I say the magnetic field is circular like this, then you can curl your hand and say, oh yeah, this definitely needs a current carrying conductor with the current coming out, right? That's the only way this circular magnetic field can be created. Right? If I just give you this diagram and ask you what is the source of it, you can confidently say it's a current carrying conductor right in the middle. So the magnetic field is created by this conductor, then you can apply the thumb rule to create this. But here the magnetic field is created by an independent magnet, and the coil is something totally independent of it. Right? It's going to experience this magnetic field, but that is not the source. The current in this coil is not the source of this magnetic field. Right? So the curling your hand, that doesn't apply in this case. Anybody else? What is the relationship between EMF and flux? E equal to d phi by dt. Is that it? Perfect. And what does that minus sign signify? What was the reason we put that in my minus sign? The Lenz's law, right? What does it say in simple terms?
Opposes the change in flux.
Perfect. So if I have this coil which is moving, and if I were to connect this, close out this coil with some resistor or even short it for that matter, then this coil is going to start to get a current in it in such a way that it opposes the change in the coil's flux, right? So I'm initially like this at 45 degree. As I start to go from 45 degree to say towards 90 degree, what is happening to the flux in this coil? Is it increasing or is it reducing? Increasing, because when it's at 0 degree, flux to the coil is 0, B dot ds, right? Dot product. When it's at 90 degree, flux is at its maximum. So going from 0 to 90 degree, the flux is continuing to increase. So as alpha goes from 0 degree to 90 degree, the flux in the coil is increasing. What does our Lenz law say? An EMF should be created such that if I close the circuit out, it will create a current in such a way to reduce the increasing flux, right? What should be the current direction in this coil so that the flux starts to reduce? Perfect. So if the current were to flow through in this direction, right? Now, Thomas, you can use your right hand rule, right? You curl your hand around this loop, the B field would be like this. So my coil is like this, right? So let me, if I show it to you like this, so let's say the magnet, your eyes are the magnet and the north pole, and this is the south pole, the both side. And the current, if I were to flow like this, so the magnetic field due to the magnet is coming from you towards the board. Due to the current carrying conductor, it's coming from the board towards you, right? So as the flux increases, because the coil is moving due to the external magnet, the current through this coil would be in such a way that it creates a magnetic field that is opposite to the external magnetic field. So as this flux increases, the current in this coil would be such that it would try to reduce the flux. So this is the flux due to the magnet, and the flux due to the current in the coil should be such that it goes down so that this increasing thing does not happen as this coil sees it. So if I were to put a resistance here, would the current flow in the correct direction for the polarity of the EMF that I've drawn? If this is positive, this is negative,
Oh, yes.
current would go through the correct way, right? So it would go from positive to negative in the external world. Internally, it has to satisfy KCL to complete the loop, right? So that's all the negative sign says. So the EMF that I drew here is perfectly correct. So going back to our thing, so if I don't have this resistance, there would still be an EMF developed, right? Because the charges are going to get moved because of this moving conductor and a magnetic field. As we saw, the derivation itself comes from two fundamental laws. In this case, it will come from F equal to QEB, right? So the EMF is going to get developed. So in this case, let's say we don't connect anything to the outside world, we go put a multimeter and measure this. The terminal voltage will be the same as the EMF across this coil, right? But we can apply an external voltage as well to the system. So let's say I apply some voltage here, right? Let's say because of this rotation, the EMF is 20 volts. And externally through the battery, let's say through some DC power supply, let's say I'm applying 30 volts. Would this be a problem? Yeah, sure.
Or, sorry, this is just about the EMF from before. You could also write it in the opposite direction, right? And then say it was increasing.
Write it in the
Like if you flip the polarity, that would still be like, you
If
could
I
still,
put positive here, negative here.
you could still do that. You just have to flip the sign of the derivative, right? Or the,
You mean if I put the EMF in this direction, positive here, negative here?
yeah, and just said like it was like then the EMF would be increasing, right?
No, the problem is if I put it in this way, right, and I put a resistor here, the current would be in the opposite direction. If the flux is starting to increase, so the external flux in this case, so the current will start to flow in this coil, that flux is going to be the same direction as the magnet's flux. Right, so if I did it in that way, the coil is going to add on to the external magnetic field. Now there is a problem because of this, because some of these two is what is interacting with this coil now. That would then lead to even more increasing EMF. Right, the phi would increase further. And then that would then again increase the coil current because the EMF increased, which would increase the coil current, which would increase the flux due to the coil, which would then again increase the EMF. There will become an infinite loop. Right? The negative sign on the Lenz's law is basically to prevent that infinite energy loop from forming.
Sorry, I guess I'm just confused because if you do the right-hand rule, like
Here comes everything.
the lines are like going in the same direction, right?
Yeah, it's the same thing that he's talking about. Like, which side is the wire, like the area, like normal in the photodiagram?
So let's say this is the north is your.
But like in that one, like is the right conductor on the far side?
Oh no, so yeah, right conductor is closer to the south pole. Right conductor is closer to the south pole. The left conductor is closer to the north pole.
Oh, okay.
So the coil is
That makes a lot
oriented
more
like
sense.
this. Right, so this is the right conductor. This is the left conductor. Right, so it's increasing.
So the terminals are basically coming like straight out,
Yeah,
not down.
terminals are coming straight out.
Okay.
Right, yeah, so these are so this is the case where we have the rotor and we're looking through the rotor. And my 3D rendering is offered. Was it your question as well, Jonah?
Yeah, I think so.
Okay. If you're not clear, let me know.
I guess I'm like, regardless of which orientation it is, wouldn't the flux lines be in the same direction as the B field, like in this orientation?
Regardless of which one are you talking about the current, or are you talking about the EMF, or are you talking about the terminal?
Like if you do like the induced magnetic field from the coil,
Yep.
isn't that in the same direction as the B field from the magnet?
No, it depends on the direction of the current. So okay. So let's say this is a coil, right? If the current is going like this, curl your hand around, the B field is opposite to the magnet. If the current is instead going like this, you would curl it, B field would be in the opposite direction. Right? So if I had a current carrying conductor, like if the coil has current like this versus the coil having current like this, in this case, the magnetic field would be outwards. In this case, the magnetic field will be inwards. Assuming this is the current. Here, when I do it, was B field with the current inside. But yeah, so if I had like a current in a circular coil, think of a solenoid, right? You're looking at it from the top. Let's say the current is going in this anti-clockwise direction. The B field would be coming out of the solenoid. If you had a solenoid in which current is going in the clockwise direction, the B field would be going into the solenoid. Right? Yeah, depending on the direction of the current, the polarity of the B field, just curl your hand around, right? If you curl it like this, it'll be like this. If you curl it the other way around, it'll be like this. Right? Does that answer you? Okay. Any other questions? Okay. So going back to our thing, if I were to apply a DC voltage here, positive voltage, negative voltage. Let's say I apply 30 volts, but this coil is rotating with some speed because I already said it's some Ke times omega. So depending on some speed, the back EMF can be anything. Let's say it's 20 volts. Will this be a problem if the EMF is 20 volts while the voltage that I apply externally is 30 volts?
Would they superimpose?
Would they superimpose? Everything that we have modeled here is linear. They will superimpose, but what are the terms that are involved? Can I put two voltage sources in parallel? No, right? Is this wrong? Is there something else in our circuit that we are not modeling here? So the EMF, when previously I spoke about it, right, I looked at two open terminals and I was measuring the voltage across it, which I said is equal to the EMF. But what happens is when you have a coil like this, let's say I have a coil like this, and there is a magnetic field varying through this coil, there is going to be an EMF developed across this coil. At which point will you draw the EMF across?
You need a bunch of them,
Was it?
like every point.
Every point, perfect. So those of you who have done power system course, you know that we do these clump network models, right? When we have a transmission line, we put this L and inductance and resistance to represent hundreds of miles of transmission line. But in reality, it's like tiny elements where the voltage is being dropped across the transmission line. Same thing happens here. The EMF is not developed at one single point and lost in a clumped way in some particular point, right? That's the way we draw it to simplify our analysis. But in reality, tiny sections of the conductor, as the B field is varying across this loop, so this is a loop of conductor short circuited, and the B field is varying in this loop, there's going to be an EMF developed across this loop. But every tiny section develops a tiny EMF that is dropped within that section itself. So the resistance and inductance of that section itself drops that EMF that's developed across it. So when we have this network, the way we will draw it is in this clump network model, where we'll say the voltage applied externally is some terminal voltage V. And then we'll model the whole coil as some inductor and some resistor. And then we'll say there is an EMF that's developed across it, which again, I'll put it in a clump network model with some capital E. Right? So I can have a different terminal voltage compared to what the EMF generated is. Now, if I were to open the circuit out, right, there can be no current through this. So whatever voltage I measure here is same as measuring the EMF. Right? But the minute I close this network, there is going to be current flowing through this. I can no longer measure the EMF once the closed circuit is closed with an external voltage source. There is no way of figuring out what the internal EMF voltage is. Of course, if I know what the current is, if I know in the inductance and the resistance, I can mathematically calculate it. But if I don't know these parameters, there is no way I can tell what the EMF is just by looking at the terminal voltage, because terminal voltage is something you put in to the system. And then the EMF is actually, if you actually really want to draw the system, it's going to be some tiny inductance, some tiny resistance, some tiny EMF, some tiny inductance, some tiny resistance, some tiny EMF, right? So, and these are infinitesimally small, tending towards zero. So you have these tiny sections of the coil where voltage is developed, voltage is dropped, voltage is developed, voltage is dropped, voltage is developed, voltage is dropped. We just like to clump all of these components together, put one big LS, put one big RS, and say, oh, there's a big EMF. So these two are completely different terms. If you open this out, you can measure the EMF by measuring the terminal voltage. But the minute you're connected, there's nothing you can do about it, right? Christopher, does it explain it? The difference between EMF and terminal voltage.
So what happens then when your voltage is 30 and your EMF is 20?
So the current will start to increase, right? The current is going to increase. Then what is going to happen? If the current increases in the mechanical system, what will happen? What is current related to in the mechanical system of a DC motor? The torque increases. If the torque increases, what happens to the speed?
Accelerates.
Accelerates. If it accelerates, what happens to the EMF?
It gets bigger.
It gets bigger until the point where they balance out.
Okay.
It will reach a steady state. So you apply a larger voltage. That's the reason why the motor accelerated every time we step the voltage. It's because of this difference. Current increases, torque increases, speed increases, EMF increases until they reach a steady state point. Okay. Any other questions? So this was our model. Can somebody give me an example of a pure frictional load? We looked the whole bunch of different loads, right? Or I shouldn't say pure frictional load, mostly frictional. What kind of load would that be? Rollers. So when you have rollers, right? Or if you have a fan which is rotating at low speed, or if you have a span rotating at high speed, but we have idealized it to be B omega instead of B omega squared. Not idealized it, linearized it. Right? So we have, so let's take a case where the load torque doesn't exist, just for simplicity. And we have, in case of a fan, let's say low speed, right? We have B omega, just to keep the design challenge a little bit bigger than just solving simple B omega. Let's say this fan has some inertia as well. Right? Not an unreasonable assumption given the long radius of the fan blades. Okay. So let me give you the value for the, let me say, 0.01 Newton meter second per radian. And inertia doesn't matter, let's say some 200 micro kg meter square, and this torque is 1 Newton meter. So so let's say this is the mechanical, we have a fan and we have connected to a DC motor. Let's say I apply a sudden increase in the step torque of 1 Newton meter. If I step the torque coming from the generator by stepping the current, what will be the steady state speed of the system? How do you figure out what the steady state speed is? What is the definition of steady state in a DC network?
Nothing changes with time.
Nothing changes with time, so all derivative terms goes to zero, right? So if I ask for the steady state, it's pretty straightforward. Just make this term zero. The steady state value is just the torque divided by whatever your B value is. So your omega, that's what is going to go and settle down to. I hope everybody can solve this in the time domain as well, right? So the expression would end up looking like this for the speed. And the omega value is going to be the steady state value. So tau step, whatever that was, step magnitude divided by B times 1 minus e power minus t by tau. It means a different value, capital T, because I don't want to confuse with torque tau. And this T is J by D, right? So you should be comfortable deriving this and substituting the values and getting the different responses. Okay, let's say instead of, I apply a step and after a long time, once it is very close to steady state, I make it go to zero. What will the response be? Can anybody give me the equation? What will happen to the speed? So I step the speed, it has this exponential response which has this equation. Now if I make this torque go to zero, what will happen to the speed? That's a 1 second answer.
Goes to zero.
Was it?
Decrease.
Decrease equation?
Same as what you have, but you don't have the 1 minus in front of the E.
Perfect, perfect. So it's going to start from the steady state speed, which is this part, right? Because this goes to infinity, this term drops out, it's tau step by B. And then afterwards, it just drops exponentially. So whatever Jack said, right? So we have the steady state value, and then this part just decays exponentially. Right? So this we haven't done in the homework or things, but this is what it would look like if the response goes to zero. Okay. What would happen if I am varying this on and off, on and off? What do you go about solving it? Let's say the torque. So we looked at a very simple case where we stepped it up, we stepped it down. But let's say I've gone crazy and I keep doing this again and again. What would the speed look like? How would you derive the expression for the speed in this case? What would you use?
The average.
The average is, okay, let's start off with the average. What will be the steady state speed? Let's say this is 1 Newton meter, 0 Newton meter. It's 1 Newton meter for half a second, 0 Newton meter for half a second. What will be the average speed, the omega average? How do you figure out the averages? So it's just going to be the average of the torque divided by the B value again. So omega average is going to be tau average divided by friction B. Right? Can anybody tell me why this term doesn't contribute again to the average?
It'll decrease as much as it increases over time.
Perfect. Another way of saying this, the average is the steady state value in some sense, right? On which you're having the harmonic component oscillate on top of it. This only, the d omega by dt only acts on the harmonic components. because that's the only thing that's changing. If you have a constant value, the d omega by dt, again, same as the steady state logic, when we put it in average model, this term goes to 0. So the average value is just tau average is just b times w average. That's about it. So you've already given the answer of how to solve it. How will we solve it? Let's say, so you've gotten the average value, but I want the actual response. So the response would look like this. It will be quite complicated to get the equation in transient. It's steady state straightforward. But in any case, how will I get this equation? How will I get this value? This equation is exactly the same as what we have seen before, but in a different network, that's all. If I give you the other way of looking at this equation, you'll give me the answer right away. V equal to L di by dt plus R times I. If I tell you the voltage is varying like this and I ask you to find the current, how will you find the current? What would you use? Laplace. We can use Laplace. Is there any other way? When we have repeating periodic signal, what did we learn?
Use Fourier.
Was it
Use the DC plus the Fourier for the components.
DC plus the Fourier coefficient? So you can just split it into our voltage into some DC component, and then some first order, second order, third order, fourth order, fifth order, sixth order, so on and so forth. Right? Find out the Fourier coefficients for it. Pass it through the. So when we had the voltage, the currents for the different Fourier coefficients would have been R square plus omega L square, n omega L square. For different Fourier coefficients, find the currents, and you'll also need to get the phase angle as well. That is very important. Omega n times omega L divided by R. Right? And then sum of those sinusoidal current, and you will end up with this waveform that we have here. Right? So this equation is exactly the same as our electrical system. Just because it's a different equation, that doesn't mean we can't use a system of solving that we have learned already. Right? And the nice thing about going with Fourier is I can have more and more complicated models as well, which might get too complicated to solve using Laplace. So I can have a waveform like this, and then this can go up like this, go down like this, go up like this. This would get a little bit tricky to solve with Laplace. Not too hard. You can still apply superposition and decompose it into a triangle and a step waveform. Just because it's a linear circuit, you are good with doing that. And in this case, you can still solve it, but it would be much easier to just get the Fourier of all these kind of signals and solve it straightforward. Okay. So talking about Fourier, go to a circuit that made us use Fourier in the first place. So we had an inductive circuit with some resistive network. And once I close this, by now everybody should know this expression, right? V by R, 1 minus e power minus t by tau. Tau is L by R. Can I open the switch? I cannot, right? When the current is flowing. What was the solution?
Open it slowly.
Open it slowly. That would still be interrupting the current, right? There would still be some V equal to L di by dt. So one solution is making this dt term very large. So the voltage that's generated across this is not large enough. What is the problem with opening it very slowly though? Let's say I want to create this kind of on and off pulses, right? If I want to, let's say my voltage is 100 volts and on an average I want 50 volts here. That means half the time I close the switch on, half the time I turn the switch off, I can get an average of 50 volts, right? But the problem is I need to do this very slowly. So what will happen if I do this very slowly? My current is going to look like, has a lot of ripple in it, right? It goes up too long, comes down for too long, goes up too long. But as I keep increasing the switching frequency, as this n omega term goes higher and higher, the component of the current that has that harmonic content is going to become smaller and smaller. So I want to intentionally switch this as fast as possible. That's the reason in power electronics we are trying to go to higher and higher frequency. We're never satisfied. Now we can switch up to a megahertz and we're still not satisfied, we want to go higher. Because we can go higher, then the ripple in this current becomes smaller and smaller, and that in turn has its own advantages. What would this ripple cost? Let's say this inductor is wound on an iron core. What is the ripple current going to cost in the inductor?
Torque?
No, in an inductor. When you have a current that's changing sinusoidally in an inductor, what is going to be the problem with it? An iron core inductor, not an air core.
Lossy.
What,
I don't know, I said lossy.
what loss?
Is that hysteresis?
Hysteresis loss. So when we looked at our BH curve of our iron core, has the shape. Right? So this is directly proportional to the current that we apply. And as we keep increasing the current, reducing it, so when the current varies sinusoidally, H varies sinusoidally as well, but the B does this loop, right? So whatever is the area inside this loop, that is totally lost, that cannot be recovered. That's the hysteresis loss. So whatever these harmonic components are, these are actually going to be lost as a hysteretic loss in your inductor. That is not recovered, that's not useful in any way, right? And it's going to start to heat up your iron core of your inductor. In addition, it's going to make your converter very lossy and inefficient. So you want to go to as high a switching frequency as possible, so that you can reduce the harmonic content in your current, so that you can reduce your losses and make it more efficient, so on and so forth. And there are other issues as well, like EMI, EMC that comes out because of these large varying waveforms. We don't need to worry about it too much. Okay, so you want to go to higher switching frequency. What is the solution then?
Diode.
The diode.
What was that equation that you wrote with the V over rad R squared plus? I don't make.
Which one? This one?
The tan -1.
Oh. So the current, let's say you have a voltage source, some nth harmonic voltage source, right? Sine n omega t connected to, because we can apply superposition to this network, right? Once we resolve it into Fourier components. The current through this is going to be I equal to the voltage across it, the magnitude of the voltage, the nth component that we get divided by the impedance, which is going to be R square. And this is the inductance. The impedance of it is going to be n omega, the frequency, right? N omega times L. So n omega L, the whole square. And the angle of it, of the current, is going to be n omega L divided by R. What does that angle signify? So if our voltage is plotted like this, right? If this is our voltage, our current is going to be phase shifted. This is our current, and the phase shift between the current and the voltage is that angle. Right? Let's call this theta. The difference between the delay and the current is the phase angle phi. Okay? Does it answer you? So we can put a diode. What is the problem with the diode? Quite lossy. So it drops about, let's say, a power diode could drop about 0.7 to 1.2 volts when it's conducting. And if you have 50 amperes of current, that's 50 watt of power drop right there. It's a thermal management issue and of course efficiency issue. So what is the solution? There are two solutions that we discussed. What can we replace the diode with?
Transistor.
A transistor. Another solution?
Schottky diode.
Schottky diode. So we can replace this with the Schottky diode, right? Which would be low voltage drop, about 0.2 to 0.3. So what is the limitation of a Schottky diode? High leakage. Another limitation?
Low breakdown.
Low breakdown voltage. In this case, the leakage is not that much of an issue. It's going to reduce the efficiency a little bit, but not significantly. But the bigger problem is you can't get it for, let's say, breakdown voltage of typically less than 100 volts. So that's a very big limitation on Schottky, and typically when you have these converters operating at higher voltages, you cannot use a Schottky diode, in which case you need to put a transistor there as well. And all MOSFETs come with a body diode, whether you like it or not. Right? So the top one also is going to be a MOSFET. I'm not going to draw this, but the same thing replicated there, so that we can go to much higher switching frequencies, so that the currents are smoother, so that the harmonics are lesser, so that the hysteretic loss doesn't happen here. and we replace the bottom diode with a switch so that it can again operate more efficiently, right? So once we replace this with a switch, this is called a synchronous buck converter. I might go a little bit longer than 215, maybe 220, 225. Those of you have to leave, that's absolutely fine. The video is recorded. It'll be available on Zoom. So leave anytime you want, right? Until I cover all the topics, I'm just going to stay here and continue. Okay, so once we have this synchronous buck converter, whenever our principle was when the top switch is on, the bottom switch is off. So when we have, let's say the top, so again, I'm going to draw it in this form. Same thing as before, but these are no MOSFETs with the body diode inbuilt into them. Right, so our principle is if switch 1 is on, switch 2 is off. Switch 1 is on, switch 2 is off. And when switch 2 is on, switch 1 is off. Can both switch 1 and switch 2 be off at the same time? Is that a valid state? So first question is that a valid state, and is it a necessary state? Second question. Can both the switches be on at the same time? All right, so that's straightforward because once we turn both on, we are going to have a shoot through, which are basically shorting the source, which is problematic. Can we have both of them off?
I mean, you can if there's no current going through the inductor.
Right? If there is current going through, you can't turn them off.
It'll conduct through the body node.
Was it?
It'll conduct through the body node.
Connect through the body layer. It's absolutely fine. You can have both of them off, even when there is current through. You'll just conduct through the body diode when you use a MOSFET, right? So that's absolutely okay. And it's a necessary state too, because when I have switch 1 on, switch 2 off, and I go to switch 2 on, switch 2 off, in between, I need to have some time period. So switch 1 is on, it's going to off. And then I have switch 2, which is previously off. It cannot instantaneously turn on. It needs to wait for some time for the switch 2 to turn on. Because during the time, even though the switch had turned on, the charge carriers would not have cleared, the current would still be conducting. It would gradually die down. So during the time period, you do not want to turn on the bottom switch because the current will then jump through this path and short the whole system. So during the time, you need some dead time. So where both switches are off. So when both S1 and S2 is off, it's called dead time. So that the current can commute from one switch to the other switch, fully other body diode, and then you turn on the switch. Do you need to turn on the switch at all, or body diode is fine?
You get lower losses if you turn it on.
You'll get lower losses. So the objective must be to minimize the dead time as much as possible. You don't want this to be too long. Because if you have this too long, then the body diode will be very lossy. You want to avoid that. That's why we put the switch in the first place. But it is needed for a short portion of time, but you want to avoid it as much as possible. Okay, so going back to our network there, let's say instead of putting an inductor, I give you a circuit with a capacitor. Thank you. Let's say instead of this, let's say I had a switch, I had a capacitor. Do I need a diode in this case? Or can I freely turn on and turn off as I wish? What will be the expression for the current once I close the switch? What will be the steady state current? Right? As soon as you turn this on, the capacitor offers zero impedance. Right? But at steady state, capacitor offers infinite impedance. If you have a capacitor, the steady state current through the capacitor is zero. So our equation is going to end up being so V divided by S once you take Laplace of it. And then we have 1 by S. Let me write the time equation. V equal to 1 by C integral I dt plus R times I. So if I apply a step in the voltage, that's V by S. equal to 1 by Cs times I of s plus R times I of s. Right? And then again you can solve for the Laplace of it, and the current value would come out to be I of t equal to V by R times e power minus t by tau, where tau is your time constant RC. So the expression for the current would look like, initially as soon as you close the switch, the current would be equal to V by R, and then it will start to decay all the way down to zero. As time goes to infinity, the current in the network will go to zero. Right? So the in this case, you can easily open the switch, no problem. You don't need any diode or none of those. Right? Okay. Now let's say I give you a little bit more complicated circuit where I have some inductor and some capacitor, and I'm applying this kind of pulse voltage. And I've resolved them into Fourier components. So the pulse voltage, I've resolved it into different Fourier components, and if I ask you for the current magnitudes, so I've resolved them into different VNs. What will be the current? Vn divided by square root of. Can you really start filling the terms for me? When you have L, C, and R, all three in the circuit. This is a first year circuit theory class, right? What was the impedance of an LCR network? Same R square. We have our omega L. And then for the capacitor,
1 over omega c.
1 over omega C. What's going to come in between? Plus or negative?
Yes.
Negative. So that's the only way we can explain resonance, right? Because if you get the correct frequencies, these two terms will cancel out and the network would have maximum amount of current. The capacitor components will equally cancel out the reactive impedance component. So, and again, of course, n term should be there, depending on which nth component you're considering. So this is a very big problem in power electronic networks, because anytime we wind an inductor on an iron core, or any core for that matter, we have one coil here and there, and we said that it needs to be jam-packed as close and tightly wound as possible. That is an advantage in one way, that's a very big disadvantage in another way, because you have created a winding and another winding right next to it. What you have created is a parallel plate capacitor. You have a coil of metal coil here, a metal coil here, separated by some distance, by some varnish, which is a very good insulator, and that's going to create basically a parallel plate of some form. So whenever you have an inductor, it's going to have its own parasitic capacitance. So that is called a parasitic capacitance. So whenever you have an inductor, there is going to be some tiny parasitic capacitance associated with it. But the problem is when you have low frequency components, that's not a problem. But when you have very high frequency components, the impedance of a capacitor starts to reduce as you go to higher and higher frequencies. Right? Previously, when you had an inductor, as you went to higher and higher frequency component, the impedance increased, so the current went down. So if N went up, I went down for an inductor. But for a capacitor, as N increases, I goes up for a capacitor. So as your circuit becomes more and more capacitor, the current will start to increase as you go to higher and higher switching frequencies. So this parasitic component has a very big problem, where so any inductor that you take from, say, you buy some inductor from DigiKey, and they would typically tell you it's rated for 400 kilohertz operation. You take that inductor and put it in a converter that's operating at 10 megahertz, it will not behave like an inductor, it will behave mostly like a capacitor at that point. So you would assume that the current ripple would reduce, but actually current ripple would go crazy when you operate, because you're not putting an inductor in that case, you're putting a capacitor effectively. So whenever you have an inductor capacitor combination, this would end up being your effective impedance, right? And if you get to a point where the frequency correctly matches the resonance, then this whole term vanishes. It's purely resistor, which will typically be very low in circuits, and then you get a very large current in your network, which will burn out the network. Right? We take 5 more minutes. Again, those of you have to leave, that's absolutely fine. Okay, so when it comes to magnetic circuits, magnetic lecture, we had basically 3 formulas. That's all the whole derivations were. So flux is surface integral, flux over a closed loop is 0, our integral h dot dl over a closed loop must be equal to ni. We gave a new term for this, mmf, and then the final is negative n d phi by dt. Again, we already analyzed what this negative term comes into picture is, just to make sure the energy doesn't go crazy. And then our final equation, force was L times I cross B. Okay, so let's look at a couple of cases. In the homework, I gave this simple case that we had an air gap and had a coil. If I give you the current, what will be the direction of the magnetic field for this coil? How will you figure out the direction of the magnetic field? Perfect. Then curl your hand around. You have your B field, right? What will be the direction of the H field?
Opposite,
Opposite.
opposite,
Why is it opposite?
don't recall.
Opposite.
I don't recall.
Okay. What is the relationship between B and H for ion and air gap? Well, let's start with the simple case. What's the relationship between B and H and an air gap?
Constant.
And what is the constant?
You're not?
Mu naught. So B was just mu naught times H, right? And in ion, that would have been mu R, mu naught times H. We introduced this H term instead of B term is because we do not know what this mu R is for different material. It's very hard to figure it out for a single particular value. So we have those BH curves, elaborate systems, and so on and so forth that can model it as if it's a constant. So both for ion and air gap, B and H have the same polarity, right? B is in one direction, H is going to be in the same direction. So H is like this. And what is going to be the direction of the B field in the air gap? Is it going to be in the same direction as the ion? Or is it going to be in a different direction?
Some of it will go outside, but
Right?
Like-
Let's assume fringing. No fringing. Right? So if there's no fringing, it's going to be in the same direction, right? How will you explain the reason why it's in the same direction? So whenever I ask for explanation, it has to go back to the 4 fundamental equations, no other options. Why would it be in the same direction?
if you drew like a box through the air gap, all the field lines coming in would have to come out.
So if I were to draw a box encompassing some area of the ion, some area of the air gap, whatever field line came in must be the field lines that go out. If the field lines were to reverse here, that would be problematic because all field lines come in. That means we have proven the existence of a monopole, which is not possible, right? So that's easy, and let's try and solve this. So let's say I have some relative permeability mu r for this, and I've given you some length L of the core, and then L of the air gap, Lg. How will I go about solving it? What are the two equations that I need to solve it? Solve the B field in the air gap. So if I give you this problem where I have a n set of conductors and I have some current flowing in this coil and I want you to find out what the B in this air gap is, I've given you the length of the air gap, I've given you the length of the core, the mean length of the core, and then I've given you the relative permeability of the core. What are the equations you would use? There are only two equations you can use. Okay? So how will you employ them? The first one, go over a closed loop, integral h dot dl is equal to ni. So if I go over this loop that I've chosen, h in the core times length of the core plus h in the air gap times length of the air gap must be equal to ni. And then the second equation is surface integral over a closed surface, b dot ds must be 0. What does that mean? The flux coming here must be the same as the flux going out here. And our flux itself is going to be equal to, what is the formula for our flux going to be? I've given all the dimensions. Let's say I've given the cross section of the iron core, cross section of the air gap. What is the flux going to be?
Yeah.
B times A. B times the cross sectional area. So BM, AM, sorry, B core, A core must be equal to B air gap, A air gap must be equal to a common flux phi. We know the relationship between B core and H, which was H core times mu r mu naught. This also we know is mu naught times H in the air gap. Right? So we have two equations, two unknowns, Hg, Hc, Hc, Hg, right? So we can substitute back all of those together, solve for two equations, two unknowns. We can solve for one of them, HG or NC, whichever you choose. And then once we know that, we can solve for BC or BG, whichever you want to solve, right? Any questions on this? Okay. So how do we get the reluctance? Anybody remember the formula for the reluctance of the air gap?
Oh, yeah.
So it has the same formula as resistance. So resistance of a wire would be, don't memorize it. If a wire has longer length, the resistance is going to be longer. So the length has to be on the numerator. Straightforward. If the cross-sectional area of the conductor increases, then the resistance starts to drop because the current has more pathway to flow through. So the area has to be in the denominator. Then one another term, mu r, mu naught, right? Similar to conductivity. Conductivity in your material would come there. Here we are going to produce permeability of the material instead of conductivity. That's about it, right? So again, if I were to memorize all these formula, I can't definitely remember them. Okay. Can you tell me what the relationship between reluctance? Okay, so once I have this for different material, I can figure out the reluctance. So let's say I have a more complicated structure like the one I gave you in the homework. Right? Let me complicate it further. There's a bunch of air gaps. Then this, of course, as you saw in the homework, we can model it as an equivalent electrical network with some Ni and then some reluctance R1, R2, reluctance of the air gap, reluctance of the air gap, R3, R4. Right? And then I can figure out what the current is going to be in this network, and the current will be equivalent to what in the magnetic circuit? Flux. This would be the flux in which position in this diagram? The left leg, center leg, or the right leg? Right? So flux here is going to be the same as flux here. Right? Flux is the same. Is the B field going to be same though?
Not necessarily if the area changes.
Alright, perfect. So the flux here is the same as the flux here, because whatever flux goes in must be the flux that leaves out, but the B field needn't be the same though. So depending on the cross-sectional area through which this flux is cutting through, when we mentioned the flux is B times the cross-sectional area, right? So if the cross-sectional area changes, the flux will be the same, but the B starts to change. What will be the H in the iron core? For the circuit that I've drawn here, what is the H in the iron core? Okay. Yeah. Okay. I thought you made a zero symbol. So it is. So here, when I drew a wire here, that means I meant the core has zero reluctance, right? How can a core get zero reluctance if mu r is infinite? Right? If mu r is infinite, for a given B field, what is H going to be? H is going to be B divided by mu r mu naught. So H in the core would be zero. So the way I've drawn it, I've assumed an ideal conductor here. That means I've idealized the core. That means H is going to be zero in the core. And then the rest of it, you can find out. If I were to ask you the inductance of this network, well, how will you figure it out? So instead of telling some current is flowing in this conductor, in the exam, let's say I complicate this and I give you an voltage source. V is some 10 sine 2 pi 60t, 60 hertz sine wave. And then you are required to figure out what the current is and what the flux is. Can I give a DC voltage here in this network? The way I've drawn it, all ideal. Can I put a DC voltage source?
Flux would go to 0, right?
Would flux go to 0? What will it go to?
Some constant value
Would it be constant?
for a DC source.
Yeah, for a DC source. What is this if I were to draw it in an ideal circuit manner? What would this whole thing be drawn as? What have I created here? It's an iron core with some coil on top of it. What is that?
Inductor,
An inductor. If I put a DC voltage to an inductor, what's going to happen to the current?
you get a current ramp.
Current is going to ramp. It's going to go to infinity. Right? What is going to happen to the B field? Would that also go to infinity?
Saturate.
It will saturate. So if I were to give you the BH curve of the material, and if I say that I put a DC voltage source, the current would go to infinity. So the current would ramp on, keep on going up and up and up. What will be the slope of this current? So for some current with time, what will be the slope of this current?
Is the inductance?
Inductance. Okay.
Is the x-axis time or flux?
X-axis is your time. LdI by dt. Because this would have been 1 by, sorry, V equal to LdI by dt. Right, your I would have been V by L times time. So whatever, so V over L. Okay, so this current is going to keep on increasing, but your B field will initially start to increase linearly, but then it will saturate out, because that will be the center curve, exactly that curve, right? Because this was H versus B, which is same as I versus B. And if you linearly increase I, that's just traveling along this axis, which is same as increasing the B field. So your I versus B. So B would end up saturating your core. Okay. So for all of this, you need to know the inductance to figure out what the slope at which the current is going to rise. How will you find out the inductance of the circuit? Magnetic circuit is quite a complicated circuit.
Is it inverse to the reluctance?
Perfect. Is it just the inverse?
I think there's like something in the numerator too.
Right. So the textbook has given the formula. But again, don't memorize formula because in the exam you'll just spend whole lot of time searching for them. And you will run out of time. So let me give you the formula, but the derivation is so straightforward though. N squared divided by R. So we have two equations that we have already derived. This is something we can easily remember, L di by dt from circuit course. You must have known that. And then the other one is N d phi by dt. This is our EMF equation. Right? So let me equate them both. L di by dt is equal to N d phi by dt. What is our flux in terms of MMF and reluctance? The answer is right there on the magnetic circuit.
Ni over R net.
Ni over R. So flux is just the MMF, right? The voltage source in our magnetic circuit divided by the reluctance R. So substitute there, you have N, and this N comes out becoming N squared. The reluctance is a constant term that doesn't change in this magnetic circuit because nothing is moving. And then d phi by dt becomes di by dt. Right? Cancel these two terms out. Here L equal to N squared by R. Right? So again, if you just remember these two, you'll be able to derive it. But there is a roundabout way of doing it as well. This is for the easy case. But in more complicated networks where the system itself is moving around, let's say there's a small segment in the magnetic circuit is moving back and forth, and you want to find out the variable inductance. In which case, what will you do? What is the other way of figuring out the same thing? You can go around and find the magnetic field in each of the add gap. Right? Once we know the magnetic field, you can figure out the energy in the magnetic field. B squared divided by 2 mu naught times the cross-sectional volume. That's the times the volume over which it's spread out. And once you have energy, that is equal to, for an inductor, what's the formula? F Li square. So figure out what the total energy UV times the volume for each of those air gap sections, sum them up, that must be equal to half Li square. And that L would be exactly the same as this one that you end up deriving. This R is the R effective in your magnetic circuit, right? The final thing is with the magnet, with that will be done. So the same magnetic circuit, let's introduce a magnet into this. So again, in the homework, we did a very simple case. I put a magnet here. So before I forget, sorry, there's one more thing that I want to talk about. When we talk about torque and so on and so forth in our mechanical system, when I drew this diagram, I drew the torque like this. This is a convention we use in motors. This is not a physics convention. In physics convention, what will be the direction of the torque? Okay. So if the system is rotating like this, the perpendicular direction is the direction of the torque. All right, that's the vector. If you are drawing a vector for the torque, it's actually this direction coming outwards. Because your hand anti-clockwise is considered positive, so that will be the direction. In our case, we draw it like this because of the fact that it's a two-dimensional system. It has only one axis of freedom, right? That is the only axis over which it can rotate. So it makes no additional information saying that, hey, this is the direction of rotation, because we already know for a mechanical rotor motor, that's the only degree of freedom. But if you had like a box, like some kind of thing that can rotate in three-dimensional sphere, you would, so let's say this is rotating like this, then the torque would look like this, right? You can resolve it into X component, Y component, Z component. So you have three-dimensional torque. It's a vector quantity. So whenever I ask for torque in machines textbook in the class, we are going to assume it like this, but this is not how the physics convention would be. All right, same with speed as well, omega m. So in homework, whoever said it's along the axis, perfectly correct physics-wise. That will also give you full points, or drawing it like this in what we do in machines. That will also give you the correct points. Okay. So getting back to here, let's say the magnet north is here, south is here. What is going to be the direction of the magnetic field inside the magnet? Upwards or downwards? Upwards. Thank you, Ben. What is going to be the direction of the magnetic field in the core here? Upwards, downwards? Upwards. Thank you, other Ben. Your vote should sit a little bit far away. And in the air gap, the B is going to be the same direction. Right? We already saw that. Let's not complicate that section. So sorry, B core, B magnet. Let's get to the interesting part. What is going to be the H field in the air gap? Same direction, opposite direction? Same. Again, we saw the relation. H is just B divided by mu naught for the air gap. In the iron core, same direction, opposite direction. Same, right? It was the same formula. It just became B core, C core, mu naught, mu 1. So nothing changed. H in the core. How about in the magnet? Same direction, opposite direction? Same. When I draw the BH curve for the magnet, in the homework, did I give you the first quadrant BH curve or the second quadrant BH curve for a magnet? Second quadrant. Right, I only gave you this portion. Actually, the magnet curve extends all the way. Okay, going all the way like this and coming out. We are only interested in the second quadrant operation, because the way our circuit came out, our equations, when I write down the equation for this, it is going to be equal to, let's assume the core is infinite permeability, mu r is infinite. That means I can ignore the core. So it's H magnet, L magnet plus H air gap, L air gap equal to 0. So HM was equal to negative HG, LG divided by LM. So the HM always comes out to be negative quantity the way we are operating our circuit. So HM is negative, our BM is positive. So our HM and BM, once you substitute into the equation for the other one, would be BM AM is equal to BG AG, right? Is equal to some constant flux. Again, you can substitute for this with mu naught HG. Can you substitute this with HM? When we solve our magnet, this circuit, can I replace BM as mu r mu naught HM? Thomas is saying yes.
I think so, right? I don't know, I wasn't really following, so.
All right, no worries. We can't do that, right? Because in the case of iron and air gap, we assume the B versus H relationship is linear. But here I have given you a graph which clearly shows it's a non-linear relationship. So you cannot just directly say BM is some HM divided by mu naught mu, HM times mu naught mu r. Because mu r is not a fixed value, it changes. The slope here changes. Slope here is 0, very close to 0. Slope here is quite large. Here it gets even larger. So the slope is what the mu r value is indicating. So that just keep on changing. You can't just substitute it. And that's the reason we have to go and draw these load lines and figure out where the intercept is and so on and so forth. Right? So you would take this equation, substitute back into this equation, get a linear equation, draw the load line wherever it intersects the BH curve. That is the value where your magnet B field is going to be, and the H field is going to be negative. So in a magnet, the HM is opposite BM. Okay? So it does kind of get sometimes confusing. So B core, H core in the same direction, but HM, BM flips around. So when we think of B, we kind of link it up with flux, and we think of water flow. And of course, we know from intuition that if water is flowing like this, it can't suddenly reverse inside some kind of pipe. Right? There's nothing magical happening here that can reverse it. But HC on the other hand does not. That's why I don't want to attribute it as a real field in any sense. It's a pure mathematical invention. As you can see, there's nothing physical you can associate with where H is going like this and suddenly it just reverses direction inside the magnet. Right? Okay, so let's say I add one more coil to this. Some current Ni. Would you be able to solve this BH curve solution for this? If I now again ask you for the B value in the air gap. Would you be able to solve? It's a solvable problem or unsolvable problem? Do we have too many unknowns? No. So all the changes as this equation becomes Ni, right? Because we go around this loop and integrate the H field, that must be equal to Ni. In the previous case, we didn't have any current carrying conductor, so the term was 0. Now we have some current carrying conductor, so the term becomes Ni. All right, and then again you can go through the same process, solve it. What will happen to the load line? Will it remain in the same spot? Will its slope change?
Will just get shifted.
Perfect. It's just going to move. And previously our equation would have come out to y equal to mx, right? Where this is some h, this is some b. Now we are, sorry, this is b, this is h. Once you solve for that, you'll just end up with an equation which is y equal to mx plus c. The h-intercept would have changed. That's all this additional term does. So it moves the axis around in the other direction. So if I ask you to, if I give you this coil and give you some winding, and I ask you that this is the B field that I would get without this coil, but I want to increase the B field to some particular value, then what does Ni value must be? You can do the reverse calculation. Draw a line to, let's say I want the B field without the coil is 1.05 Tesla. But I say I want actually 1.2 Tesla in the air gap. What current should I pass through this coil? Right? It's a reverse problem. Draw a load line passing through this 1.2 Tesla. Find out this y-intercept, substitute it back at here, find out what the Ni value is going to be, then you can find out what the I value is going to be, right? It's going to be a little bit more complicated, but that's about it. With that, I think we covered all topics that will be relevant for the exam. Anybody have any questions? All right, if not, we'll see you on Friday. You can come early for the exam if you have time. I will hand out the exam before, whenever you come in. You can keep reading the questions and you can start writing at 1 o'clock. Right?
Why don't you have to consider the core when you're adding the additional coil? Like why would you keep the relative permittivity as infinite?
If I give the relative permeability as infinite, then you can ignore it.
Okay.
If I don't give it, that will also get added. That will be a slightly more complicated HCLC.
Okay.
But it won't complicate it too much though. Because HC is again a function of direct, right? Flux divided by mu r times area.
Thank you.
Isn't inductance also flux divided by current?
Inductance is flux. It is flux linkage divided by current.
So could you use that?
Yes, you can. No, that's not directly flux. I haven't introduced this term just yet. It's flux linkage. So there's another term lambda, flux linkage, which is equal to Li. So I equal to lambda by L. Lambda itself is n times phi. Because it matters if, let's say, you have 3 turns versus 10 turns. The number of coils the flux links matters when it comes to the inductance.
And you just get that from integrating that equation.
Integrating, yeah.
You ever want to wrap a coil around a magnet?
Wrap.
Like if you put the Ni around the magnet, would that kind of use?
Increasing the magnetic field. I don't think so. Because typically either you would have an electromagnet or so even in a DC motor, right, you can have a physical magnet, or you can have a winding that creates the magnetic field.
Yeah.
If you have designed a structure such that it is going to take a winding on it, it wouldn't make sense to stick a magnet on it. If you have designed a structure that takes a magnet on it, you won't have space to put the winding on it. So combining both, I don't think will make financial sense just for a couple of increases.
It'd also be really complicated, right? Because it would be like the magnetic field from the coil would affect the like effective you are, right?
No. When we are looking at the magnet, we are not going to talk about mu r at all.
Okay.
Right? There is another problem. You don't get any advantage because the way I've drawn it, it looks as the amount of Ni you need is very tiny. But if you remember from the BH curve of a neodymium magnet, it's about like 900 kiloampere per meter where the coercivity is. Towards the top point, let's say you're already at 1.05 Tesla. To go from 1.05 Tesla to 1.1 Tesla to push the magnet in the direction, you'd have to put so much current in the other coil that would just not make sense.
Okay, yeah,
It
because
would
the
just make sense to take the magnet out and just put the coil with the current.
point of this is to make like a constant magnetic field in BG, right?
Yep.
Okay.
Yeah, because the magnet actually, as I mentioned, like the neodymium magnet behaves like an air gap.
Yeah.
Right, so when you put an external coil, this magnet appears like a large air gap added on this air gap. So if you're creating a magnetic circuit with an external conductor, it would make sense to make this completely iron.
That makes sense.
Because this offers a lot of reluctance.
Got it. Thank you.
One more time, to find the load line, you just say VM equals, some value times HM, basically. And then that's your line.
Yeah.
And what do you say happens when, like, I know it shifts over, why does the load line shift over again? It's just constant.
Yeah, so this expression, right? Then Ni will just show up as constant times LC by AG, some other terms.
Okay.